All right, next thing I want to do with change of variables is find the volume of an ellipsoid. So here's a general ellipsoid, and let's maybe remind ourselves of what that looks like. That just means it's a sphere kind of stretched, so kind of like a football. There's that x length is A, that y length is B, that z length is C, and then we're going to have some sort of spherical-ish thing. I don't know if I can make a good picture. Watermelon, football, something like that. Okay. And I don't know if you tried this Part B quiz question or if anyone in your group presented it, but if you try to find the volume of an ellipsoid, there are ways. We already had of finding volume of an ellipsoid from Math 126 using double integrals, but if you tried to do it with spherical coordinates, which it feels like you should be able to do, because spherical coordinates are about round things. This is a roundish thing. It feels like you should be able to do it, but the problem is spherical coordinates go out in spheres, and then like the intersection of a sphere and an ellipsoid is actually like kind of a weird ellipse thing, and suddenly you don't know where to start and stop, and you can't get the bounds right, and it's super, super annoying. I was very annoyed when I first found that I could not find the volume of an ellipsoid by integrating in spherical coordinates. So like it feels like you need something different. It feels like spherical and cylindrical coordinates aren't enough. You need to be able to customize it. And you can. We can make ellipsoidal coordinates. So instead of, here's my spherical coordinates, x equals r sine phi cos theta, not r, rho, let's call it rho. Y equals rho sine phi sine theta, and z equals rho cosine phi. I should probably write z there. Rho cosine phi. That's spherical. We can customize these if we just multiply it by a, b, and c. I've now stretched my sphere to be an ellipsoid. So call these. This is not an official thing, but if I were to give it a name, it would be ellipsoidal coordinates. And like, okay, so we can calculate the Jacobian. I'm a little too lazy to do that. So I copied my Jacobian over from the spherical coordinates, and all that's going to happen is all my x's are going to get multiplied by a, all my y's are going to get multiplied by b, z's are going to get multiplied by c. 0 times c is still 0, so I won't mess with the last one. And then I just do the same calculation. But in the calculation of the determinant, it'll be the same, right? The z will be multiplied by c. Every term in the determinant has a z, an a, and a b in it, an extra z, a, and b, right? So the determinant of the Jacobian, all the same stuff will happen. I'll have that factoring. I'll get the sine squared theta plus cos squared theta, all that, except everything will be multiplied by ABC. So you can check this arithmetic if you don't believe me, but the determinant of the Jacobian will be ABC rho squared sine phi, which means if I want to find the volume of this ellipsoid, I just need to integrate over the whole ellipse. 1 times, there's the determinant of the Jacobian showing up here, rho squared sine phi, and then d rho, d phi, d theta, and then the whole ellipsoid, right? So rho is going to go from 0 to, if I made rho go from 0 to 1, and then these sines and cosines were their max values of 1, I would end up with the extreme points of the ellipsoid, right? So I can make rho go from 0 to 1. Phi go from 0 to pi, because phi is still angle. We're going to be stretched in some dimensions, so modified angle with the positive z-axis is still true. And theta, same thing. Modified horizontal plane angle with the positive x-axis. Okay, and then I've already done this calculation before. This is, aside, if I take this ABC out in front, then this is the volume of a sphere of radius 1. Right, so what I'm going to get is I'm going to get ABC times volume of a sphere with radius 1. You're welcome to do the integration, but 4/3 pi r cubed, where r is 1. So volume of an ellipsoid with some calculations skipped, is 4/3 pi ABC. And you can do that easily if you make your own coordinate system. You don't have to look at any square roots or any ugly things like that.